Today's lecture is about multivariate random variables. So this is going to extend some of the ideas. We're going to really quickly go through some of the ideas that we talked about for univariate and then bivariate random variables. And we're going to extend them to more than two random variables at a time. So let's start with a really kind of basic definition of a multivariate. MB for multivariate, RB for random variable, a multivariate random variable. And if I have univariate random variables, x1, x2, all the way up to some x sub n, if x1 to xn are random variables, then we can look at x, and I'm going to put a tilde under it, so x tilde, x under tilde, which is going to be basically a vector, x1, x2, all the way up to xn, so some column vector, or I could write it as the transpose of a row vector, or x1, x2, all the way up to xn transpose. This is called a multivariate random variable, or more simply, a random vector. And this is the topic of today's lecture. We're basically going to go through and talk about many of the concepts that we've seen so far in this course, but talk about them with respect to multivariate random variables. So first of all, let's talk about the concept of a PMF or PDF for multivariate random variables. If my x sub i's, so x1, x2 up to xn, are discrete, then the joint PMF, which I'm going to write as f of little x under tilde. So up here, my kind of bold x tilde is a random variable. And here, my little x under tilde, x tilde is just a number. It's a vector in Rn. The joint PDF of my discrete x sub i's is a function from Rn. So it takes in x tilde, or you could write it as f of x1, x2, x3, etc. up to xn. That is defined as the probability that x1 is little x1, x2 is little x2, etc. all the way up to bold xn is little xn. Right, and so we can say, note that my joint PMF is a function from Rn to R. Takes in the values of my n random variables, and this is f here. It spits out the probability of being at that point. The continuous case, kind of similarly, the continuous case is if my x sub i's are continuous, then we can define what's called a joint PDF. Not surprisingly, the joint PDF is defined as a function f takes in numbers in Rn, spits out probabilities, or spits out densities, joint density in R, so that if I have some set A, some subset of my real n-dimensional space. And if I want to calculate the probability that my random vector is in this set A, so this is the probability that my random vector is in A, which you could write as, another way of thinking about this is the probability that x1, x2, x3, all the way up to xn, say transpose if you want, is in my set A. So A is some subset of this n-dimensional space. My joint PDF is the function, so that if I want to calculate this probability, what I do is I integrate over A f over A. So that's kind of my notation. This is an iterated integral, an n-dimensional integral, let's say. So this is the integral of f over A. This is kind of my notation. This would be, in our case, we would have n integrals, and we'd be integrating fx1 to etc. all the way xn, dx1, dx2, dxn, right? So it's that iterated integral there, right? But that's kind of so implicitly how my joint PDF is defined. And it plays very much the same role. You know, I'm not going to go into all the little nitty-gritty details of this. We've talked about these kind of things in the univariate case and the bivariate case, and they behave very, very similarly in the multivariate case. So we have a PMF, we'll have a PDF, and we could define things like expectation of a multivariate random variable. So, for example, if I have a function g, that goes Rn to R, I could talk about the expected value of g of x tilde. So I can talk about the expected value of g of my random variable, right? The random variable kind of lives in some sense in Rn, so I can look at a function g that maps it down to R, and then we have effectively a univariate random variable, and I can look at the expected value of that thing. And not surprisingly, there are two cases. We have our discrete case, and we have our continuous case. And in discrete case, what I do is I look at g of x1 to xn times f x1 xn. So f is my PMF, g is that function. And what I'm going to do is I'm going to sum over x1, sum over x2, sum over xn. So we have this kind of iterated summation where we sum over all values of x1 and x2 and up to xn, we sum g times f. Right, and this is just an extension of the univariate and the bivariate case. And in the continuous case, we'd have our n integrals of g of x1 to xn times f of x1 to xn times and integrate with respect to x1 all the way up to xn. It's a little bit cumbersome notation, but it's pretty much just the kind of natural extension of expectation. And that's pretty much the theme of this lecture. So not really too much new in this lecture. It's kind of just making you aware that most of the stuff we talked about in 2 dimensions can be extended up into n dimensions. We'll talk about a couple places where it gets a little bit more complicated with n dimensions, but pretty much it's just, okay, if you could do it with 2, you could tack on some other things. For instance, we'll call this a theorem. We could talk about the marginal distributions now. And in the bivariate case, we had 2 potential marginal distributions. We had bivariate x and y, we had the marginal of x and the marginal of y. Now we have a bunch of random variables. So we could talk about the marginal distribution of, say, xi. And a theorem says that the marginal distribution of xi is, and we could say denote it as f xi of little xi. In the bivariate case, if I wanted the marginal of one, I integrated out or I summed out the other. And so we had, again, a discrete case, and we had a continuous case. And in the discrete case, if you wanted the marginal of x, I'd sum over the joint over y. In this case, now you're going to sum over everything but x sub I. So I'm going to sum over x1, sum over x2, all the way up to summing over xi minus 1. Not going to sum over x sub I. I'm going to sum over xi plus 1, all the way up to summing over x sub n. And what am I summing? I'm going to sum up my joint distribution. So it's very, very much straight up generalization of the bivariate case, where I would sum over just the one other one in the bivariate case. Now we sum over everything but x sub I. Or in the continuous case, I would do lots of my integrals, and I would integrate my joint distribution with respect to x1 all the way up to xi minus 1, skip x sub I, integrate over xi plus 1 all the way up to xn. Okay. We can then, for example, we could talk about conditional distributions. We had talked about this recently. So one thing you can do with a marginal distribution is you can get the conditional distributions. And so in the bivariate case, we had f of x given y, or y given x. Now in the multivariate case, we can kind of take any subsets and condition on any other subset. So the way I'm going to write this is I'm going to say that if I have two sequences of random variables, let's say xi1, xi2, all the way up to xim, for example, and some other sequence. The notation, again, is a little cumbersome, but let's say xj1, xj2, all the way up to, I don't know, xjk, right? So these are potentially different sequences. They're different lengths. They're just, I'm picking some of the indices for one and some of them for the other. Then the conditional distribution of, let's say, the, and when I say distribution, I should really say either PMF or PDF. The conditional PMF or PDF of xi1 to xim given xj1 to xjk is, so a little cumbersome. The way I'm going to write it is f of xi1 dot 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 xim bar xj1 xjk. So it's the conditional distribution of the first group given the second is going to be the joint of the two sets. So it's the joint PMF or PDF of the first, so f of I1 to IM, xj1 to jk over the marginal, or the joint of the second, let's call it xj1 xjk. Whew, a lot of notation there. But it's really not that complicated of an idea. And if I want to take one set of random variables here and condition on another, then I take the joint of all of them together and divide through by the joint of just the one set. Or you call it the marginal of that set. The line between kind of marginal and joint gets a little blurred with multivariate random variables. Okay. Let's pause here and look at an example. We've covered a couple concepts. It's a bit dry, but let's look at some examples. So let x1, x2, x3, and x4 have a joint PDF of, so my joint PDF, f of x1, oh boy, let's write it all out, x2, x3, x4 is going to be 3/4 x1 squared plus x2 squared plus x3 squared plus x4 squared. And this is going to be non-zero as long as each of these x sub i's is between 0 and 1. So you can think about it as like this 4-dimensional cube that it has a distribution over, and the distribution is 3/4 times x1 squared plus 2 squared plus 3 squared plus 4 squared, right? Now, one thing that has to be true, and you can check for yourself, and again, I'm not going to write down every single fact about multivariate random variables, but most of the facts, I'm going to give you kind of a smattering of facts, and the other kind of facts are that you know are true for kind of univariate and bivariate are also going to be true for multivariate. For example, you should check that if I integrate this thing, x1 to x4, if I integrate it over x1 to x4, so I do this kind of quadruple integral, that should be 1. All right, and really I'm integrating x1 goes 0 to 1, x2 goes 0 to 1, x3 goes 0 and x4 goes 0 to 1. If I integrate this function, this f, that should give you 1. It's positive, it should integrate to 1. So the kind of usual facts that we had in the univariate and bivariate case are also going to be true. So this is a joint PDF of a 4-dimensional random vector. And you could ask, say, if I gave you this, I could say, what's the probability, I don't know, x1 is less than half, x2 is less than 3/4, and x4 is bigger than 1/2. So how would I calculate this, right? What I have to do is I have to integrate. I'm going to end up doing 4 integrals. I have to integrate over the area. So somehow this defines some region A. And basically I have to do this integral, and the region I'm going to integrate over is going to be whatever A is. So A is the set where it's, so they're all between 0 and 1. So like x1 is between 0 and 1/2, x2 is 0 and 3/4, x4 is bigger than 1/2, and x3 is whatever. And what I'm integrating is I'm integrating the joint PDF, which is 3/4 times the sum of the squares of these things. And I got to integrate dx1, dx2, dx3, dx4. So let's just set up, let's not do the whole integration problem, it's a good exercise. But let's just set up the limits of the integration, okay? So first integral, the innermost is with respect to x1. x1 goes, well, they're all between 0 and 1. x1 goes up to 1/2, so that should be from 0 to 1/2. x2 goes 0 to 3/4. x3 can be whatever, so it can go all the way from 0 to 1, because that's kind of the limits of where that has a non-zero density. And x4 can be bigger than 1/2, so it goes 1/2, and the upper limit is 1. So that's going to be the integral you have to solve. There's a Calc 3 problem in there for you, and I'll give you the answer for you to check against, but you might pause and try to just do that. This integral should give you 3/256. That's kind of something you can calculate now, right? I've given you now multiple random variables, and I told you something about their joint distribution, and I could ask you a probability statement about them. Probability x1 is less than 1/2, x2 is less than 3/4, and x4 is bigger than 1/2. Other kind of questions I could ask. Let's look at some other kind of questions we could answer. Maybe I want the joint PDF of x1 and x2. So I want f of x1, x2. And I know that to get the joint of x1 and x2, I mean, we haven't kind of explicitly said this, but if I want, when we talked about our marginal up here, we said, well, if I want the marginal of just one of these, I sum or integrate over all the other ones. Well, if I want, in my case, the marginal of x1 and x2, I should sum and integrate over everything but, or I should, in this case, integrate because it's continuous. I should integrate over everything but x1 and x2. So what I'll do is I'll integrate over x3 and x4. And what do we integrate? We integrate that joint. So, well, what's the joint? Let's just write. The joint is 3/4 times the sum of the squares. Right? And the limits of my integration are 0 and 1 because I know my random variables are all bounded between 0 and 1. And so that will give me the kind of joint of x1 and x2. You also call it the marginal of x1 and x2. I mean, so these tend to kind of blend together a little bit. But the point being is I want the PDF of x1 and x2 together, and I'm given the PDF of x1, 2, and 3, and 4. I integrate out 3 and 4. So I integrate the PDF, the joint PDF, over 3 and 4 over the entire allowable range. So again, here is a fun Calc 3 problem. You could pause it at this point. What you'll get, if you do this, is 1/2 plus 3/4 x1 squared plus x2 squared. Notice it doesn't involve x3 and x4. We integrated those out. Other things I could ask about, I could say, we had talked about expectation. So I could look at the expected value of, say, x1 and x2. And now we actually have multiple ways of calculating this, right? I could calculate it given the joint PDF of all 4 of them, because this is a function of x1 to x4, just a function that only involves x1 and x2. Or, since I actually right up here got my joint of x1 and x2, I could directly go from that. So let me just write out the 2 possible ways. One would be, I would say, I would integrate 4 times, and my function, my g, is x1 times x2, and you could integrate my joint, this multiplied by my joint PDF of all 4, across all 4 of these, right? And all of these would all go from 0 to 1. Or, and it should be somewhat obvious why this is, well, maybe not too obvious, but you can think about why this is equivalent. I just derived, theoretically, if you actually did the Calc 3 problem, gotten the joint of x1 and x2, so you could instead just say this is the integral. I'm just going to use the joint of x1 and x2, and my function is still just x1 times x2, but now I'm going to use this joint. I'll multiply by my joint distribution of just x1 and x2, and that will give you the same thing, right? Because effectively, all you have to do is just rearrange the integrals, and you'll get one result from the other. In any case, either way you want to do it here, again, I'll let you pause it, do the little Calc 3 problem, and I'll give you the answer here. It's 5/16. It's not too bad of a Calc 3 problem. It's definitely doable, if a little tedious. Okay. So finally, we've talked about conditional distributions. down. Conditional distributions what is the conditional distribution of, let's do something fun. Let's say x3 and x4 given x1 and x2. So this would be f of x3 and x4 given x1 and x2. Why did I choose this one? Because the conditional distribution is going to be the joint of all of them over the marginal of what I'm conditioning on, which is x1 and x2. And I know that from the previous problem. So that the joint of all four of them is 3/4 plus the sum of the squares. Oh boy. And that marginal of x1 and x2 is 1/2 plus 3/4 x1 squared plus x2 squared. And so this is the conditional distribution of x3 and 4 given x1 and 2. Cool. Cool, cool, cool. Okay, let's talk about some other concepts. Not in the greatest amount of detail, but let's just go through some other concepts here that are true and that can be extended to the multivariate case. And basically, you've done all the hard work at this point. You've learned the bivariate case, and going from univariate to bivariate is really where the hard work is. Bivariate to multivariate is pretty straightforward. Let's talk about mutual independence. So we say, I'm going to give you the definition, the technical definition, then we'll talk about the useful theorems, that x1 to xn are mutually, that's not how you spell mutually, mutually independent if for any sets A1, A2, A3, all the way up to AN. So these are going to be subsets of the real line here. For any selection of these, if I look at the probability that x1 is an A1, x2 is an A2, all the way up to xn is an AN, if I can factor this whole lecture is basically a lot of writing, just a lot of notation, but basically factorization that you think I should be able to do, period. So that's the theorem, right? We say that x1 to xn are mutually independent if for any sets, a1, a2, up to an, so these are going to be sets of the real line, if the probability x1 is an a1 and x2 is an a2 and x3 is an a3 up to whatever, is just the product of probably x1 is an a1 and x2 is an, a1 and x2 is an a2 and x3 is an a3, etc. We say they're mutually independent. So this is the definition of mutual independence, and again, this is similar to our bivariate case, it's just more than 2 now. Of course, as we saw in the bivariate case, this is not particularly a useful way. Not always, occasionally it is, but not the most useful way. Practically, our kind of independence theorem is that our random variables, oh boy, let's write legibly, x1 to xn are mutually independent if and only if either my joint distribution, my joint PMF or PDF, can be factored as the product of the marginals dot x and or you can similarly define a joint CDF. I really haven't actually defined this yet, but I'm going to leave it up to you to imagine that this is pretty much the same kind of joint CDF, kind of extension of our bivariate CDF. If I can do that factorization, then my x sub n's are independent. So either I can factor the joint, this is the joint PMF or PDF, or even though we haven't really talked about it, CDF. If I can do this factorization, they're dependent. And if they're independent, that factorization holds. And this is always the practical way of checking for independence. If the joint is the product of the marginals, either in PMF, PDF, or for CDF, then we have independence. And if they're independent, then we can do that. So that's a really practically powerful theorem, and is abused a whole lot in 452. And in the next lecture, we'll talk about this even more. But that's kind of a really powerful way to characterize independence for random variables. And it's just a kind of straightforward generalization, again, of our bivariate case. So hopefully this theorem is just a nice review of some of the stuff that we've learned so far in the univariate and bivariate cases. And now it's just a little more complicated because we have a couple more random variables, but it's like going from 2 dimensions to 3 dimensions. Once you go from 1 to 2 dimensions, calculus from 1 dimension to 2 dimensions, it's easy to go to 3 or 4 or 5 or 10 dimensions, right? Okay. So let's talk about some theorems of independence. And again, these are things we have seen before in the bivariate case, and it's true again in the multivariate case. Basically, all the proofs in the bivariate case don't really rely on anything about them being really bivariate. If my random variables xi are independent, and we have a series of real valued functions, g1, g2, etc. So I'll just generically say gi is a kind of associated real valued function. Then a couple things are true. One, gi of xi, this collection, are independent. So if I just apply a kind of real valued function to each of these things kind of marginally, they're independent. And we saw that in the bivariate case also, right? Where if I apply a function to just x and just y, those functions are independent of each other if x and y are independent. And 2, if I look at, say, the expected value of g1 of x1 times g2 of x2 times gn of xn, this can be factored as a product. Expected value g1 x1 times the expected value of gn times xn. So yeah, you can factor products of independent random variables factor. We saw that in the bivariate case. The expected value of the product of independent random variables factors, and that is true for the multivariate case. A corollary of this kind of expectation factorization theorem is that the MGF of sums of independent random variables has a really nice form. So let's say the corollary talks about the MGF, the moment generating function of a sum of independent random variables. Now, we've only ever defined moment generating functions for univariate random variables. There is a way to kind of extend it to multivariate random variables. Not really quite as useful. Theoretically, you can talk about it. It's not really that useful. Typically, we only talk about MGFs for univariate random variables. But if I take a multivariate random variable and I sum up its components, so let's say, let's choose a different color. Let's say let xi be mutually independent. So xi are mutually independent. Let's define z to be the sum of my x sub I. So I take up the components of my multivariate random variable, my random vector, and I sum the components up. Say comma, then I could look at the MGF of z. Z's are a univariate random variable. It's the sum of a bunch of univariate random variables. It is a univariate random variable. So we can talk about its moment generating function. That's totally normal kind of thing to talk about. The moment generating function of z is going to be the product mx1 of t times mx2 of t time mxn of t. Just the product of all these. We're going to write this in what we're going to call product notation. So I'm going to say pi, I goes 1 to n of mxi of t. So as an aside here, right, if I have, I can write a1 plus a2 plus an using sigma notation, right? Sigma I goes 1 to n of a sub I, right? If I want to write product of a1 times a2 times a3 times an, I can write, instead of sigma, s for sum, I'd write pi. Pi for product, I goes 1 to n of a sub I. So this is just a shorthand notation, so I don't have to write out everything. This is just the product. It's called product notation. Pi notation, sigma notation. It's just a shorthand. So I'll write something like this. But this is the theorem, is that the moment generating function of the sum of a bunch of random variables, if they're independent, it is the product of the MGFs of the individual random variables. We can actually do a proof of this. Ooh. It's been a while since we've done a proof. Let's look at a proof. It's not too bad. So we want the moment generating function of z, right? If you can think back about what the MGF of z is, it's e to the tz. Expected value of e to the tz. But we know something about what z is. Z is the sum of the x sub i's. So I can replace z with the sum of the x sub i's. And I have some rules about exponents. The exponent of a sum is the product of the exponent. So I could bring out this as, so e to the t times the sum is the same thing as the product of e to the t x sub I, right? This is just a generalization of the rule where e to the a plus b is e to the a times e to the b, right? This is just a little more cumbersome because we're talking about summations. We're just using fancy sigma and pi notation, but that's exactly what it is. The exponent of the sum is the product of the exponents. And so here I basically have, back into my theorem, I have a product, the expected value of the product of a bunch of things that are independent. And so because these things are independent, I can just pull that product out. It's the expected value of the product of a bunch of independent things is the product of the expected values, right? So I can pull that product out. You can only do that when the things are independent, but we kind of assumed in the theorem that these x sub I are mutually independent. And when I do that, I can break up the product, the expected value of the product, and the product of the expected values. So I can do that kind of fun trick there. And we just have to notice that each of these is exactly the definition of the moment generating function of x sub I. The MGF of x sub I is expected value of e to the t x sub I. And that was the theorem, that the moment generating function of my sum is the product of the moment generating function of each of the random variables individually. There are some kind of follow-on theorems to this. Oh, let's just write down, we won't go and kind of formally prove them, some follow-on theorems of things you can prove with this. Follow-on is that if we have AI and BI, we have a series of these are constants. So A1 to AN and B1 to BN. And I define Z to instead just of being just the sum of the x sub I, it's AI plus BI xi. It's the sum of AI plus BI xi. You can prove, and maybe that's a good exercise, going to pause and prove a really similar theorem, which is that the moment generating function of this Z would be e to the t times the sum of the BI times the product of the moment generating functions of x sub I evaluated to at. This is basically the univariate case. In the univariate case, we saw that the moment generating function of a plus bx was e. Did I write this correctly? Should be e to the at. I think I wrote this wrong. Okay, so the univariate case, let's check ourselves. The moment generating function of a plus bx should be e to the at times the moment generating function of x at bt. And so in this case, I think I just flipped a and b. Should be the sum of the a sub I times the product of the moment generating functions evaluated at bi. Yeah, that seems right. Okay. And that basically, so it's a good gut check, that it's kind of just a generalization of the univariate theorem. So for example, let's just grab a different color here. Example is that if I wanted to prove this theorem, which I think we stated before but maybe didn't prove, which is that I have a bunch of, maybe we only did this maybe in the bivariate case. If I have a bunch of x sub i's that are normal mu I sigma I squared and independent, so I have a bunch of independent normal random variables, and they have all different means and different variances potentially, and I define y to be the sum, I goes 1 to n, of ai plus bi xi. So I linearly transform each of these and I sum them up. Let me go to a new line here. This thing will also have a normal distribution, and its mean will be the sum of ai plus bi mu I, and the variance will be the sum bi squared sigma I squared. So I think we saw an example of a similar theorem in the bivariate case, but we can prove this using the previous theorem. Probably it's easiest if you actually want to try this. Do it in the 2D case, and one way to prove it is you use induction from the 2D case. Yeah, you could prove it for the 2D case, and then you could show it works for the 3D case basically by induction. You could show it worked for the n case given n minus 1 by some kind of inductive proof. Or you could generally just use that previous theorem. So that's one way to do it. The other way is once you kind of satisfy yourself there, you can actually just straight up apply this theorem. And what you notice is that basically if I look at the MGF of y, it will be the MGF of this normal distribution. And it may take a little bit of algebra to see it. Okay. So before we get to some stuff that we haven't kind of seen before, the one last topic I want to cover that we've seen kind of similar stuff with at the univariate and then the bivariate case is transformations. So I'm sure everyone's loves transformations and wants to see what happens if we amp up the fun one more time and talk not about univariate transformations, not about bivariate transformations, but multivariate transformations. So let x tilde is going to be my multivariate random vector, x1 to xn, say transpose, it doesn't really matter. And we're going to have some function g that's going to take numbers in Rn and spit out numbers in Rn. So it's going to be a n-dimensional valued function. Takes numbers from Rn to Rn. And you guessed it. Let's say u is going to be g of x. So that's my notation for saying that, u is defined as for every outcome you would get for x, you would just shove it in that n-dimensional function u. I.e., what you could say is u has n components. U sub I is some component function g sub I of x1, x2, to xn. So this g sub I is the ith component function that goes from Rn to R. So it's basically like the bivariate transformation on steroids here, right? But now we have n random variables, and we can transform them to n new random variables. And each of our new random variables could potentially be a function of all the other n random variables. But frankly, it's not really any harder than the bivariate case. At least conceptually, it's not any harder. It's a little more algebra because there are more random variables, but conceptually, it's not any more difficult. So let's just talk about the continuous case. In our continuous case, if this function g is continuous and differentiable, then the theorem is that the joint PDF of u, so fu of little u, so here little u is some number in Rn, because u is also an n-dimensional random vector. Then the joint distribution of the u, this u transformation, is the joint distribution of my x's. I'm just going to write this fx tilde, evaluated at g inverse of little u times the determinant of my Jacobian matrix. So this is pretty much exactly the same form we saw in the bivariate case, but now u, capital U and little u are n-dimensional, and capital or x tilde and whatever are n-dimensional. G inverse is now an n-dimensional inverse function, but conceptually not any more difficult. The Jacobian matrix now is going to be an n times n matrix. So J is going to be an n times n matrix where the first row is the partial derivatives of the inverse. So partial of g1 inverse with respect to u1, partial of g1 inverse with respect to u2, all the way up to the partial of g1 inverse with respect to n, right? Second row would be the partial of g2 inverse with respect to u1, partial of g2 inverse with respect to u2, etc., etc. So again, it's a Jacobian matrix. You could say that the elements, the ij element of the Jacobian matrix, so j for Jacobian, I sub little j for index, is the partial of gi inverse with respect to uj. So the rows, was that right? Yeah, the rows are the functions. Partial of g1 inverse across the first row, g2 inverse across the second row. And as I change columns, I take derivatives with respect to the different variables, different uj's. Let's look at an example of this working in practice. It's basically, so it's a more general case of the thing that we learned, the kind of two bivariate transformation theorem we talked about. So let's look at an example of how this works. Okay, so let's say let our x sub i's be IID distributed from an exponential distribution with a rate parameter lambda. So IID here is, and I think I've said this before, is independent. So my x sub i's are independent, and they have identical distributions. I independent, I identical, D distribution. So IID. So they're all independent, and they have all the same distribution. That is, they have an exponential lambda distribution. And we're going to define our transformation as follows. U1, I'm going to just define it component-wise. So generally, U is G of X tilde. U1 is going to be X1. U2 is going to be X1 plus X2. U3 is X1 plus X2 plus X3. Dot, dot, dot. Un would be the sum of all of them. So it's kind of the partial sums. Right? So U1 is the first one, U2 is the sum of the first two, U3 is the sum of the first three, etc. And that defines my transformation. This kind of implicitly defines G. You could write it down more formally. I'm not gonna kind of bother here, but so what do we need in this theorem? We need the inverse. We need G inverse. So how do I do this? I want to solve back for my x's. Well, clearly x1 is just u1. Okay? So that says g1 inverse of u is u1. So here, again, my u here is going to be my vector u1 to un. Okay? We'll put that in a box. What does my second equation say? If I want to solve back for x2, how can I get that? Well, it's x2 is u2 minus x1, but x1 is u1. So I could say this is u2 minus u1. So g2 inverse of u is u2 minus u1. Okay. That gives me g2 inverse. Do a couple more. I want x3, right? And x3 I could say is u3 minus u2. So g3 inverse of u would be u3 minus u2. All right, and you start to see the pattern. For example, gn inverse is xn minus 1 minus, it's xn minus xn minus 1. I'm sorry, not x's, u's. un minus un minus 1. Okay, so we got the inverse functions. We saw the pattern. Dot, dot, dot there. And we want our Jacobian matrix, right? So let's get J. So J, the ijth element of my Jacobian matrix is derivative of Gi inverse with respect to Uj. And so let's kind of draw out what this matrix would be. The first row is the derivatives of G1 inverse, right? G1 is just U1. So derivative of U1 with respect to U1 is 1, and 0 with respect to everything else, right? Derivative of this inverse of U1 with respect to U2 or 3, etc. is 0. Okay. Second row of my Jacobian matrix is going to be the derivatives of G2 inverse. Derivative of G2 inverse with respect to U1, negative 1. With respect to U2 is 1, and 0 for the rest of them. They don't show up. And if I go to G3, so my third row of my Jacobian is the derivatives with respect to G3, which is, with respect to U1 is 0. With respect to U2 is negative 1. And derivative of G3 inverse with respect to U3 is 1. And 0 for the rest. And basically what I'm going to get is I'm going to get this diagonal matrix with 1s down the main diagonal and negative 1s on what we'll call the kind of lower subdiagonal there. And we'll get 0 everywhere else. So this is what my Jacobian matrix will be. And surprisingly, or not surprisingly, determinants are really hard to calculate generally in the n-dimensional case. But this is pretty easy. The determinant of the Jacobian is just 1. And so indeed the absolute value of the determinant is just 1. Why? Because I have 1s, no, that's not drawn well. I have 1s down my main diagonal. And the determinant of a diagonal is the product of the diagonal elements. So actually I have a really nice case. My Jacobian matrix is a diagonal matrix. I'm sorry, it's a triangular matrix. Oop, I should not write that. I should not say it's diagonal. It's not diagonal, it's triangular. That is, all the elements are kind of the lower triangle, non-zero in the lower triangle, and 0 in the upper triangle. The determinant of a triangular diagonal matrices are triangular, but the determinant of a triangular matrix is the product of diagonals. Not something you need to memorize, but it's true in this case. Helps us out. And all the diagonal elements are 1, so the product of all of them is 1, and certainly the absolute value of that is 1. So in this case, that means basically my Jacobian doesn't show up in the formula. If we scroll back up to what the theorem says, right? The theorem says that the PDF of U is the PDF of F at G inverse evaluated or multiplied by times the absolute value determinant of the Jacobian. Well, that thing is 1. So in our case here, we just get that the joint distribution of U is the joint of X tilde evaluated at G inverse of U. So it's basically F. Well, so let's get our components. First of all, what do we need? We need the joint of our x's, but they're all independent. So I can say this is just the product of the marginals of each of the x sub i's. And all the x sub i's have the same distribution. They're all independent exponential lambda. So they all have a distribution of lambda e to the negative lambda x sub I, which we can simplify as lambda lambda e to the negative lambda times the sum of the x sub I, right? That's allowable by our rules about products and sums. And so that is our joint of the x's. That's actually a really cute little joint distribution. And so to then finally do this multivariate transformation to get the joint of u, what we do is we take our joint of the x's and we plug in the inverse. Instead of xi, we plug in gi inverse of u. So it's lambda e to the negative lambda. And then what are we plugging in this sum here? What we're plugging in is the sum. Typically it would be the sum of the x sub I, but we're plugging in the inverse. So it's gi inverse of u. It's the sum of these inverses. And what are our inverses? So this is going to be equal to g1 inverse of u plus g2 inverse of u plus dot 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 plus gn inverse of u. And we know what these are, right? We derive these up here. Here are our inverse functions. So g1 inverse is just u. This is u1, sorry. g2 inverse is u2 minus u1 plus g3 inverse is u3 minus u2, g4 inverse is u4 minus u3 plus dot 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 un minus minus 1. What happens is all of these are going to cancel. u1 cancels with negative u1, u2 cancels with negative u2, u3, negative u3. And basically all of these are going to cancel except for un. So it turns out that the only thing that's going to be left over is u sub n. And so that gives us our joint distribution, which is that it is lambda e to the negative lambda un. And the only thing we need to specify, and that's just a coincidence of how this one happens, and the only other thing we need to specify is the region over which this joint density is non-zero. So it turns out there's this condition that u1, so certainly the ui's are positive. So u1 is bigger than 0, but it's less than u2. There's an ordering that u1 is less than u2 is less than u3, etc. less than un. Why is that true? That is true because of how we defined it. u2 is u1 plus something. u3 is u2 plus something, right? And they're all positive, and so that kind of induces this ordering here. And that actually matters because if this ordering is not true, then the density is 0. So actually this ordering here matters. It's not just lambda e to the negative lambda un for all possible u's. It's only for those u's where that ordering is true, because that's kind of a condition of the transformation, and it's 0 everywhere else. So multivariate transformations can be quite difficult, but conceptually they're not much more difficult than just the bivariate transformation. Okay, so that's definitely a little doozy of a problem there. Alrighty, so in the last 10 minutes or so here, I want to just talk about some kind of extensions. Most of the lecture today has been things we saw for bivariate random variables, and basically we just said, yes, and this works for more than 2, and instead of just 1 and 2, you have 1, 2, 3, up to n, right? But none of it is conceptually very different from what we saw in the bivariate case. But there are a couple things where we can extend things in a way we haven't seen before. So let's talk about means and variances for multivariate random variables. And we could have talked about this when we did bivariate. We did a little bit, but let's talk about it kind of fully for multivariate random variables. So in our univariate case, the expected value of a univariate random variable, think back to those simpler times, is just a real number. Expected value of some random variable x is just a number. And the variance of a random variable x, back in those simpler days, is a certain expectation, so expected value of x minus its expectation squared. But that's also just a number. So they're just kind of one-dimensional numbers. In our multivariate case, and this is basically where we start mixing probability and linear algebra. In the multivariate case, we now instead have some x tilde, which is a vector, x1 to xn, say transpose, for example, right? It's a random vector. And we could talk about the expected value of x tilde. We've talked about real valued functions of this thing, but what about like some g of x tilde, where g was a real valued function? But what about the case where we talk about it just as a vector? Can we define the expected value of a vector? And not surprisingly, you basically do it in the way that you would want to do it. I'm just going to component-wise expand this out. So I'm going to say that the expected value of a random vector is the vector of the expected values. So this is a real valued random vector in Rn. So this thing is, let's say, an n-dimensional random vector, and the expected value of an n-dimensional random vector is an n-dimensional real number, or vector in Rn. So in the same way that in the univariate case, expected value is a real number, in the multivariate case, an n-dimensional random vector, the expectation is a vector. So that seems nice. What about variance? Well, variance kind of gets a little more tricky when we try to extend it. We have what is called the covariance matrix. And we saw this in terms of the bivariate normal distribution, but you can generally define this thing for any random vector, in any n-dimensional random vector. So instead of having a variance, the generalization to the random vector is called the covariance matrix. So we denote it COV of x tilde, or typically it's capital sigma. So lowercase mu is typically the expected value. Capital sigma is the matrix, and this is a n by n matrix where the ijth entry of sigma is going to be the covariance between the components xi and xj. So while the expectation generalizes from a number to an n-dimensional number, the variance generalizes from a number to an n by n matrix called the covariance matrix, and the ijth entry of that covariance matrix is called the is the covariance between these two random variables. Notice that the diagonal elements of the covariance matrix are the covariance between a random variable and itself, which we know is just the variance of that random variable. So the covariance matrix sigma has the following kind of structure. On the main diagonal, it encodes the variance of the random variables, variance of x1 and x2, all the way up to the variance of xn. And on the off diagonals, it encodes the covariances. So the 1, 2 entry is covariance of x1, x2. The 2, 1 entry is covariance of x2, x1, which is the same thing as covariance x1, x2, etc. It just has all the kind of all the kind of pairwise covariances. Notice that because, say, covariance of x1, x2 is the same thing as covariance x2, x1, this matrix is what we call a symmetric matrix. Super powerful fact. In linear algebra, symmetric matrices are really nice matrices. So the fact that this covariance matrix is symmetric is really nice. In the univariate case, we had the fact that you could write the variance of x. One weird way to write this would be x minus the expected value of x times x minus expected value of x, right? Typically what you'd write it as the expected value of x minus its expectation squared, but you could write the square as x minus ex times x minus ex. The covariance matrix you could write as the expected value of x minus, let's say covariance matrix of a random vector. So I'm going to put a tilde under it, right? Say it's of a random vector. It's x minus the expected value of x tilde times x minus the expected value of x tilde transpose. And the expected value of all that, where the outer expectation is basically element-wise expectation of the matrix. So it's basically the generalization here. So this second case is multivariate. And the univariate case is like the square, and the multivariate case is the outer product of the vector x minus the random vector x minus its expectation with itself. It's its outer product, and then we take the expectation of the whole matrix, which is just interpreted as kind of an element-wise expectation. If that seems esoteric, not super important to this course, but it's a nice little generalization that shows that the covariance matrix really is the straight-up generalization of variance to the multivariate case. Okay. So let's look at some other fun theorems about random vectors. If A is a vector in Rm, and B is a matrix in Rm by n, and x tilde is a n-dimensional random vector, say R vector. I'm going to write these without proving them. They're actually not that hard to prove, and they can be done by looking at our previous definitions and applying all the univariate theorems. If I look at the expected value of A plus B x tilde, so this is allowed, right? N-dimensional random vector, so it's a n by 1 vector. B is an m by n matrix, so my dimensions match. That will give me a vector in Rm. I can add on another vector in Rm, A. The expected value of A plus bx, now we have a linear equation, is just A plus B times the expected value of x. This is the direct generalization of the univariate case, which says that expectation is linear. We have this linearity. Talk about matrix multiplication and linear algebra, and it turns out because matrix multiplication and adding vectors and all that good stuff is linear, it plays nicely with expectation. We have kind of a similar theorem, which says that the covariance of A plus B x tilde. Now in the univariate case, it would be B squared, but we don't really have a squared for matrices of arbitrary sizes. Instead, in this case, it's B times the covariance matrix of x tilde times B transpose. And so you have B twice. This is kind of like B squared. So let me just say like B squared variance of x in the univariate case. But now we have covariance as a matrix, B is a matrix. And so the correct way to do this is B covariance, B transpose. So this is kind of just generalization of all this, throwing in some linear algebra here. Okay. And the last thing here I think we should talk about before we end here is kind of maybe the only typically named multivariate distribution, which is the multivariate normal. The multivariate normal distribution. So we say x tilde has a normal mu sigma distribution. So here mu is a vector in R, say n, and sigma is an n by n matrix. So x tilde, which is my vector, has a multivariate normal distribution if my PDF, my joint PDF of my x's, right? So x here, right? Remember the x tilde is just my vector with components of univariate random variables x1 to xn. So it has some joint distribution, f of x1 to xn. And that is, we can write it more compactly as, say, f of x tilde. So this little x tilde here, again, is my notation just for a number in Rn. Some people put a little vector arrow over it, say it's a vector. I think physics people like that, but I write a tilde. That's kind of a very statistician thing to do. The PDF, I know you're all waiting, the PDF of this thing is the following. It's 2 pi, well, that seems familiar, to the negative n over 2, determinant of sigma to the negative 1/2 times the exponential of negative 1/2 x tilde minus mu sigma inverse x tilde minus mu transpose. So that's the PDF. Let's put a box around it. And if you stare at this thing long enough, this looks a lot like the univariate. And actually, when we talked, if you go back to the lecture about the bivariate normal, I said you could write it this way in terms of mean vector in the covariance matrix because it generalizes much better. And this is exactly what I wrote for the univariate case, or for the bivariate case. It's basically exactly because it generalizes very, very easily. It's super similar to the univariate PDF. And indeed, when n is 1, it gives you exactly the univariate PDF. In the univariate PDF, I could write f of x. The univariate normal has a PDF 2 pi. You don't typically write it this way, but you could say it's 2 pi to the negative 1/2 sigma squared to the negative 1/2. So sigma squared kind of plays the role of capital sigma times the exponential of negative 1/2 x minus mu times sigma squared inverse. Again, you don't write it this way, but you could, times x minus mu. So that's a valid way of writing the univariate PDF for a normal. And when you see that, it just directly parallels with the multivariate. So the multivariate is the generalization of this. It looks a bit different. Instead of 1 over sigma squared, you have sigma inverse, because we don't write 1 over a matrix. You write the inverse of a matrix. The special case of this, of the multivariate normal, is that when mu is the 0 vector and sigma is the identity matrix, we call it the standard multivariate normal. And that's kind of like being normal 0, 1, but now we have 0 vector, and instead of the 1, we have the identity matrix. So why don't we stop there? I think we're kind of at our time there, and that's a nice place to end with a really powerful, nice distribution with the multivariate normal. And so what we've seen today is basically most of today has just been going through all of the things that we learned in the univariate case and the bivariate case, and saying, yeah, they work also for n variables. And everything we learned about bivariate, about marginals, conditionals, about transformations, with the tiniest of little tweaks, we can make this work for multivariate random variables. And basically, I've taken several weeks of lectures about bivariate things, and we've just done it in this one because we basically know most of this already.